In the previous examples, we always used functions whose input was an integer. So when we say f of n is a function of size n, it's easy. If the input is an integer, we can just take that integer. But what if there can be many different inputs with the same size? What if the input is a list? What if we have, for example, sort function, sort of L, such that the length of L is n? If we give this sort function a list that's already sorted, all it has to do is check that, and the complexity is O(n). If the list is not sorted, it has to run some sorting algorithm, and it could be n squared or n log n. So the complexity can depend on the input. So how can we do it? We can't just give one number, because there can be many different complexities. So the way to solve this is we need to take some kind of average over those inputs that we're interested in. So for example, if we take a best case, we take only those inputs of size n that give very good times, low times. So for example, in the sort function, they would give only sorted lists as input. And in the worst case, we would give examples where the sorting algorithm does as bad as possible. So in some implementations of quicksort, you can give lists that take n squared. So we'd give those lists. And in an average case, we would take the inputs according to the kinds of inputs we expect. So there's some probability distribution. So if we give random lists of integers, then the quicksort will be n log n. So there's three different ways that we solve this normally. So here's another example. Let's take the function first negative of L. It takes a list of n integers, L, and it returns the position of the first negative integer it finds. So for example, if we give it the list 5, minus 8, 6, 7, it returns the position of the minus 8, which is the second element, so it returns 2. Notice that the minus sign in Oz is represented by a tilde symbol. So in the best case, here, let's only give lists whose first element is negative, or whose the first negative element is within some constant number of positions. In that case, the complexity will be O of 1. In the worst case, well, let's give lists all of whose elements are positive except for the last element, which is negative, and then we have the worst case complexity, and it's O(n). Now in the average case, it depends on the distribution. If each element has a 1/2 chance of being negative, then we will very quickly hit a negative element, and if you make the calculation, you'll see on average we need to see 2 elements, so that's a constant, so it's O of 1. But if the position of the first negative element is a uniform distribution, so it might be the first one, it might be the second, up to the nth, and each one has probability 1 over n, then the average complexity will be n, because on average it will have to look at n over 2 elements, and n over 2 is O of n.